Ayan, anyone listening me, please unmute and respond to my question. हाँ जी हमजा, उसको देखी थी वीडियो और उसमें उस एग्जांपल को अटेम्प्ट किया, तो you got the capacity then 236 movement, 136 kilonewton meter. So anyone else?
Yes, sir.
ट्राई किया था
हाँ जी हमजा, कितनी आई थी कैपेसिटी, कितनी आई थी?
सर 136
136 क्या? किलोन्यूटन
मीटर।
किलोन्यूटन मीटर। मूवमेंट के यूनिट 136 किलोन्यूटन मीटर। और किसी ने ट्राई किया जी?
Yes, sir.
Yes,
136.
So can if I ask you to share your screen, I allow you to share your screen. So can you show me the solved example from your system? If you have prepared soft file or you have the image of that example, or you will prefer to upload the solved problem on files folder in MS Team. कोई ऐसा स्टूडेंट जिसको ये प्रॉब्लम समझ नहीं आई? Roll number 56. Please unmute and let me know, have you tried?
Yes, sir.
आपने अटेम्प्ट किया प्रॉब्लम को?
Yes, sir.
तो क्या आंसर निकला in terms of movement, resistance, capacity?
So, the 136.32 kilonewton meter.
Good. Abdul Hasib, please respond me. Abdul Hasib Ahmed.
Yes, sir.
कितना निकला जी? सारे 136 ही कह रहे हैं, किसी का 146 नहीं निकला कैपेसिटी?
सर नहीं किया।
आपने नहीं अटेम्प्ट किया?
नो सर।
ओके, व्हाई नो? आपका दिल नहीं करता PRC 1 का लेक्चर रिपीट करने का या रिव्यू करने का? हम ये आगे बशीर साहब है जी, बशीर 989 जी। बशीर,
यस सर।
किया था अटेम्प्ट?
नो सर।
व्हाई नो?
सर लास्ट लेक्चर नहीं लिया था, पता नहीं।
Okay, अच्छा, I have one suggestion. I solved that problem with section A last on Tuesday. I had 2-hour lecture with section A and I solved that problem, and its video is recorded. Online lecture video is recorded. I will upload that video on your files folder. So all of you are advised to watch that recorded video, because while solving that problem, I have discussed few more important points which are important in a way, because those will help you to consult different tables from ACI code or some ACI provisions while solving the problem I discussed, which you can also read from the textbook. Different reference books on reinforced concrete can provide you those provisions while designing or analyzing a beam. What are the important steps which are to be considered. So I will prefer to upload that recording with section A, 2-hour recording. So I suggest all of you to please watch that recorded lecture. Agreed? Otherwise, I need to attempt that example again, and I think it will be time wastage in a way, because it will be just a repetition, and by watching that video you can very easily grasp the flow chart. Agreed? किसी को इससे एतराज तो नहीं? हाँ जी, अब्दुल हसीब, अनीस मलिक, आयान परेरा, इंजीनियर बिलाल मिर्जा. So you agree with my suggestion?
वो वीडियो अपलोड कर देना सर, वहां से हम देख लेंगे.
Okay. So I shall, first thing is I will, let me just show you that video. Which is present in the files folder of section A. In files folder and in recordings, it was on today is actually April. Second, Tuesday, 3rd and 4th lecture. So it will be on April. th. ये एक फोल्डर है उबैदुल्ला.
सर वो नीचे ट्यूसडे के जो है वो डेट से इशू हो रही है, शायद वही हो.
दिस वन. हाँ, ये डिफरेंट
सर लास्ट से थर्ड नंबर, लास्ट से
जी
थर्ड
ये
नंबर.
हाँ जी बिल्कुल, ये 2 आवर्स का. ये डिफरेंट, लेकिन ये फोल्डर कैसे बन गया उबैदुल्ला? इसमें इस फोल्डर में कोई, there is no file inside. Okay.
सर आई थिंक स्टूडेंट्स भी शायद फोल्डर जो है वो बना सकते हैं, तो शायद किसी से गलती से बन गया.
Okay, okay. You are right, this file recorded on Tuesday, and little different style. Rather than mentioning date, the day is mentioned. So it is 247 MB file. So once it will be downloaded, I will upload it in your files folder. So today I then will start from lecture on balance steel ratio. So first I will talk about reinforcement ratio, and then I will discuss this little small derivation which is very important, how to determine steel ratio. balanced steel ratio. Let me start the recording. So as you mentioned that most of the students have tried to solve that example problem. So now let me start from the discussion on first what is reinforcement ratio, and then I want to derive balanced steel reinforcement ratio. I mentioned in my previous lecture that there are two cases, case 1 and case 2. Case 1 means tension controlled beam in which steel will yield, and it will yield excessively and finally concrete will crush. Case 2 is the beam in which tension steel will not yield while concrete will crush. It is also named as compression control. So the problem which I assigned you, that problem was of a beam of width 300 by depth 450, and in that problem I mentioned that there are 3 bars of size number 25, and the steel grade, suppose, of these bars is grade 300. Yield strength of these 3 bars is grade 300, and their size, their dia is number 25, and concrete in this beam was of grade 20 megapascal. So Fc prime of the 28 days compressive strength of the concrete given was 20 megapascal, reinforced with 3 number 25 bars of grade 300. So I assume that the cover from the center of the steel to the bottom of the beam, lower edge of the beam cover, is 75 millimeter. It is my selection that I selected a cover to the center of the steel layer 75 millimeter. So when I select cover 75 millimeter, I will be left with the effective depth of the cross section, which will be the distance from the top compression fiber to the center of the tension steel. We use small letter d to show this dimension, and 450 minus 75, because 450 was the gross depth, total depths, and in this 450h, if I subtract the cover, it will be d equal to h minus cover. So we will get the answer 375 millimeters. Now, in order to get idea that how much is the reinforcement area present in the cross section, so that idea that how much steel area is present in a cross section is very useful information, because this will give you a very quick understanding that how lightly or how heavily the cross section is reinforced. And we term this information in terms of a ratio, and Greek letter rho is used, and we define this ratio, unitless ratio, as reinforcement ratio, in which in numerator what area of steel is present in the cross section will be placed, and in denominator the effective area of the reinforced concrete cross section will be present. So it is the ratio between area of steel in the cross section divided by the effective area. In Flugger, you will agree that the internal lever arm capacity utilize effective depth. So the concrete below the center of the steel to the soffit of the beam is not utilized in movement resistance. So in case of calculation of reinforcement ratio in flexural members, in denominator it is recommended to use effective area. So rather than B into H, you will use B into D. And in numerator, area of steel, cross-sectional bars area, cross-sectional area of the bars will be calculated. In our example problem, we have 3 bars of grade number 25, designation number 25. So dia will be close to 25 millimeter. I will show you one design aid in ACI code where you will get for different dia bars their nominal areas, their weight per unit length along with the dia in millimeters. So for number 25 US customary bar, cross-sectional area, nominal cross-sectional area of this bar is 510 millimeters. Get this information from the design aids. It is very close to pi by 4d square. So dia is close to 25 because this is a deformed bar. There will be some deformation lugs on the surface of the bar. So it will be little more than 25. But just rough estimation can be that you can use pi by 4 into 25 square and you will get very close to the nominal area of the bars. So the standard size bar nominal area will be 510 millimeter square. So in our case, in this beam under question, under discussion, we will have 3 into 510 as area of steel in the cross section divided by the width of the cross section to the depth of the effective depth of the cross section. So how much will be the answer? Can you reply? This reinforcement ratio in this cross section, which is unitless ratio, area over area. How much will be the answer?
0.0136.
जी दोबारा प्लीज रिपीट करें.
0.0136.
Okay. 0.0136. So in terms of percentage, I can mention that the reinforcement ratio in this cross section is 1.36. The beam which we analyzed for capacity, that beam was actually case 1 beam, and that case 1 beam in which steel was at yield, when concrete crushed, we got the reinforcement ratio 1.36% in this beam. So this gives us a very good judgment that very close to 1% is the reinforcement ratio in cross section when I am getting case 1B. If you increase this reinforcement ratio to 3% in the cross section, you will start getting the behavior over reinforced or case 2. If you will keep on increasing the area of steel, finally what you will get, your section will shift from case 1 to case 2. So once you will write the equilibrium equation, you will get that steel is not at yield when concrete crushed. So you have seen in this example problem, please watch the recorded video because there are few points which I discussed with section A. So when you write the equilibrium equation of this beam, you get AS into Fy equal to 0.85 Fc prime into A into B, and you assumed that your steel is at yield. And based on this assumption in this equilibrium equation, you got A value. And probably you will get A value equal to 90 millimeter. This A value you can convert into C neutral axis depth by dividing A with beta 1. And for this grade of concrete, beta 1 will be 0.85. So once you know the C value, you can draw the strain diagram. In that strain diagram, knowing the C value and getting linear strain diagram and putting the limiting strain of concrete, the crushing limit 0.003, and knowing the C, you can get epsilon S. Because in this diagrams, you will apply similar triangles condition because the upper triangle and the lower one both are similar in this linear strain diagram, and this leg length will be D minus C. So 0.003 over C is equal to epsilon S over D minus C. So in this way, you will get epsilon S from this strain diagram. If the epsilon S comes out to be greater than or at least equal to epsilon Y, your assumption will be okay. But you selected AS FY, your assumption proved right because the A and the C, and based on that C, the strain diagram has given us the strain in the steel of magnitude what we assume in our equilibrium equation that steel will be yielded. However, if at this stage you get the answer based on your A and then C from strain diagram that epsilon S is not greater than or at least equal to epsilon Y, then you have to replace this Fy with Fs, and all your calculations are to be revised with this new equation that ASFS is equal to 0.85 Fc prime AB. And then it means now you are handling, rather than case 1, you are actually dealing with case 2. where steel will not be at yield, then concrete will approach crushing. And again, from strain diagram, with the latest C, you can get the strain in the steel, and obviously the answer finally will be that epsilon S will be less than epsilon Y, and for grade 300 steel, epsilon Y is 0.0015. So in the solution of this problem with section A, I have discussed these aspects while solving the problem. That first we wrote equilibrium equation, we got A, from A we got C, and then we confirmed that our equilibrium equation is right or wrong. Confirmation was done by checking that on that neutral axis depth, what is the status of steel. If steel is yielded, our equation is valid, and then I can get the internal capacity. So case 1 beam is easy to analyze and is ideal in design, is most desired design cross section that is under reinforced, tension control, that steel excessively yield before crushing of concrete. Because once concrete will crush, that is end of story. But we want that before crushing, lot of yielding, stretching and strain occurred in the steel bars, because this will give us warning, sag, cracking on the bottom, and we can take preventive measures, remedial actions, evacuation, or otherwise energy will be absorbed before failure rather than a brittle sudden failure, which will take place in case of over-reinforced beam, case 2 beam. So while you solve this problem, or after watching that video, you will find that students are responding me that they got MU equal to 136 kilonewton meter. So as a structural engineer, that may be a good assessment that this is the ultimate movement capacity of this beam. But if you want to tell the client that how much load this beam can take as ultimate load, then you need to convert this movement into load. I mentioned in my lecture that this beam is simply supported. This beam has a span 5 meters. So once you have the movement with you, you can very easily the simply supported maximum movement at mid span magnitude WL square over 8, compare it with your MU, because MU you have calculated is at the mid span section, which is stressed to maximum limit. So you are comparing it with the maximum movement ordinate of a simply supported beam. So in this beam, you know L, which is 5 meters, and then you can get WU. So finally, rather than reporting MU, you will report that ultimate load on this beam be this much kilonewton per meter. So when this load will be applied, concrete will approach crushing and steel will be at this much strain. So once you will get the strain of this problem, you will get the strain value more than 0.005. I remember with section A, we got epsilon S with this neutral axis depth C value greater than 0.005. So code has allowed us to use capacity reduction factor phi for such beams in which steel strain is equal to or greater than 0.005 equal to 0.9. However, if the beam will be over reinforced, case 2 beam, then code will restrict us to use phi 0.65 because the failure is brittle, so the reduction is strict, 35% reduction on the nominal capacity. And if the strain is in between epsilon y and 0.005, then linear interpolation between phi will be done. And phi can be 0.8, 0.85, 0.7, depending on the epsilon s. That will be our topic of discussion in next lecture. So this is what I have briefly revised, which I discussed with section A, but please watch that recorded video because you will get all the steps. Now, just for your information, as I mentioned that once you will consult code, and I have shared with you ACI 318-2019. So in ACI 318-2019, in Appendix B, you will get steel reinforcement information. And here you will get steel reinforcement information and different bar size numbers, ASTM standard reinforcing bars. So starting from number 10, number 13, number 16, 19, 25, which we have used in our example problem. So nominal dia given for this is 25.4 and the nominal area given is 510 millimeter square and nominal mass in kg per meter is given. In Pakistan, we normally use in our normal structures bars with dia number 10, number 13, then number 19 and 25. So mostly these four bars 10, 13, 19, 25 will be used. So I recommend you to at least memorize these four bars nominal areas because you will be mostly using them in your calculations. In FPS system, number 10 is given the number 3. Number 13 is given the number 4. Then number 19 is given the number 6. And number 25 is given the number 8. And in our local language, when I say bar size 10 in SI system and number 3 in FPS system, in our local language, we call it teen sutra. Number 10 is our laborers, they are well familiar with the local language, they call it teen sutra ki bar. Char sutra. Number 13 will be number 4 and normally they call char sutra. In their point of view, 1/8 inch is actually 1 sutra. So this is number 3, number 4, number 6, and then number 8. Number 8 means 8 sutra, 1 inch bar. So I recommend you to at least memorize these bars sizes because otherwise you need to consult again and again such design aids. And furthermore, as I have given you idea about the reinforcement ratio, and in the beam which we solved, the reinforcement ratio is around 1.36%. So this reinforcement ratio, if will be compared with some typical ratios, you will be able to classify the cross section very quickly. What those typical ratios are, one out of them is balanced steel ratio with the subscript B with rho from Greek letter. So rho with subscript B will be the symbol used, notation used for balanced steel ratio, and it is corresponding to that amount of steel in the cross section, that area of steel in the cross section, those much bars in the cross section, which will cause yielding of the steel at the same instant when concrete approaches. So it means it is very important situation, unique reinforcement ratio, which will result into crushing in concrete and yielding in steel simultaneously. It means actually when I say case 1 and case 2, case 1 means epsilon s is greater than or minimum equal to epsilon y, and case 2 is epsilon s less than epsilon y. So it means when I say epsilon s equal to epsilon y, it means it is the just start of case 2. When epsilon s is exactly equal to epsilon y, it means I am actually at the stage when my cross section has the reinforcement ratio equal to rho balanced, because when concrete crushes, tension steel was just at yield. So I am just on the boundary of case 1. And if I will get epsilon s less than epsilon y, will enter into case 2. So I can very easily state that if my rho will be greater than rho b, I will enter case 2. And if rho is equal to rho b, I am on the boundary between case 1 and case 2. I am on the boundary between desirable and undesirable behavior. So desirable means case 1, and more desirable is that epsilon s should be 0.005 or bigger when concrete crushes. So over having epsilon y, if I have over here 0.005 versus 0.003 in crushing in concrete. That is most desirable behavior of a reinforced concrete cross section, ductile and with energy absorption before failure. So this balanced steel reinforcement ratio rho B will help us to classify our cross section, because in your example problem you calculated that your reinforcement ratio is 1.36%, and for this cross section if you calculate that your reinforcement balance reinforcement ratio is suppose 2%. So once you have the information that your cross section actually has 1.36% reinforcement ratio while the balance reinforcement ratio is 2%, you can quickly comment that your section is under reinforced, tension controlled, case 1. So I need not to be puzzled at the stage of calculating the capacity. I can confidently write equilibrium equation with ASFY equal to 0.85 FC prime AB. So my T is equal to C, and in T I have no doubt, since my rho in cross section is less than rho B, so I have no doubt that steel will be at Fy when concrete will crush. Since we are capping the stress to Fy, but actually when epsilon S is greater than epsilon Y, so steel may enter the strain hardening, and the stress in the steel bar may be even more than Fy if you have crossed the yield plateau. But in USD, we will limit the stress to Fy. However, we will calculate the actual strains, and strain beyond yielding we will report, and that will be used to determine phi. But Fs, maximum stress in the steel, what we are going to use will be Fy. So in this case, rho B is a very good indicator if I have in hand the information of rho B of the cross section. So idea is simple. You will draw the linear strain diagram, and that neutral axis depth C with subscript B, which will result into simultaneous occurrence of crushing and yielding, will be termed as the balanced failure. And you will agree that its condition is still very simple, that epsilon S is epsilon Y, so Fs is Fy, and ultimate concrete strain as per ACI is fixed to 0.003. So if I want to calculate the Whitney's simplified stress block depth based compressive force in that cross section, I will be just replacing A with A subscript B, because it is to signify that actually we are working on a balanced failure. So our neutral axis depth will be against a balanced failure, and our uniform stress block depth also corresponds to balanced failure. So in our CC, compressive force resultant, we will put B as a subscript. And in writing the equilibrium equation at a section T equal to C, I will put without any doubt T equal to A as Fy, because I am just at yield. So Fs is equal to Fy. And in Fy, I am keeping it as it is, but I am going to replace that area of steel because we defined the reinforcement ratio as it is AS over BD. So if I have that area of steel which is satisfying the balanced failure, I can replace this area of steel with rho BD. I will bring that BD on the left hand side and I will put a subscript with that rho that it is actually a balanced reinforcement ratio and that area of steel is corresponding to a balanced failure. So T will be replaced with rho B, B into D. And when I will write the basic equilibrium equation on the left hand side, on the right hand side, I will keep rho B on the left hand side. B and B will cancel and it will be simplified to 0.85 ratio of the material strengths and ratio of AB over D. So I kept rho B on one side. So still in this equation, I have the requirement of knowing the material strengths in the cross section, effective depth of the cross section, and uniform stress block depth at balanced failure of the cross section. So I want to replace this AB with some terms which are easily determined, which are not unknown, so that I can determine the rho B without difficulty of first calculating the neutral axis or uniform stress block depth. So in order to replace that AB, I will take help of the strain diagram. And as we have seen earlier, for balanced steel ratio, the strain diagram should satisfy the condition that crushing and yielding simultaneously and triangles are similar. So I will write from the similar triangles base over height equal to epsilon y over d minus cb. So you may say perpendicular over base equal to perpendicular over base. Rather than base over height, you can say perpendicular over base. So I will keep CB on one side and I can bring the terms on the right hand side, and in this simplified shape I can even replace epsilon y with Fy over Es because Hooke's law is applicable up to that limit, and I will multiply the numerator and denominator with Es over Es to convert this right hand side into a stress format because strain into Es will give me the stress. So you can keep in mind in your memory either this shape or the next one in which I replaced epsilon y with Fy over Es and I multiplied numerator and denominator with Es and Es, and I converted it, the Cb into this shape, that's 600 over 600 plus Fy into D. So either this you can keep in mind or this one. Both are equally applicable. Both are giving me Cb. If I am having Cb, I can get AB because AB is beta 1 Cb. So this AB now I can put in my equation 1 and I will get the shape of rho balanced, which is very important to be kept in mind. is equal to 0.85 Fc prime over Fy beta 1 600 over 600 plus Fy, because AB has D over here, and in our equation 1 there was a D over here, so D and D cancel each other, so we are left with this equation of rho B. And look at the rho B. Rho B is depending on the material grades beta 1, which again depends on the neutral X, which depends on the concrete grade, because we learned that F average will change once we change the concrete grades, and that's it. So rho B can be easily determined without any problem. And if I now ask you that in your example problem, what you solved, can you give me rho B? So you will say 0.85 and beta 1, because we used the concrete grade 20, our steel grade was 300. For 20 grade concrete, beta 1 is 0.85 into 600 over 600 plus Fy, and Fy is 300. So can you calculate rho B of your example problem? And only you require grades of materials, strengths, and the beta 1. 0.85 into 0.85 into 20 over 300 into 600 over 600 plus 300, which will become 900. रो बी में बता सकते हैं? CR
0.0321. I think
जी
0321.
0.0321. So I may say 3.21%. And your beam, which you solved at home, has reinforcement ratio 1.36%. It is a clear message that rho of your cross section is well below rho balanced. So there is absolutely no doubt that your beam is ductile, it is tension controlled, under reinforced. So this rho will help us to classify the cross section, and we can very quickly comment on the type of cross section. So I think this derivation is also very important, and we will also discuss other typical reinforcement ratios. Not only rho balanced, the other very important reinforcement ratio is also with the subscript rho max, which is the maximum allowed, and also one other very important rho minimum, that reinforcement ratio less than this is not allowed. And rho max means that reinforcement ratio more than this will not be allowed. So we will derive rho max equation, and also we want to discuss ACI proposed rho minimum equations, empirical equations, because if steel will be less than rho minimum, your rho is less than rho minimum, chances of fracturing of the steel bars at the instant when modulus of rupture in beam will come are possible, so sudden failure can take place, which is undesirable, and crack widths will become wider if our rho is less than rho minimum. We never allow reinforcement ratio less than rho minimum. Ideal is our rho should be less than rho balanced and it should be and greater than rho minimum, and furthermore if rho is less than or equal to rho max, it is more preferred, and rho max will come somewhere over here. So on the rho chart I can say that rho balanced, if it is increasing in number, in magnitude, rho balance will be somewhere over here. Then comes rho max, maximum allowed. Don't confuse with the max means maximum rho, it is maximum allowed. And rho minimum.
एक्सक्यूज मी सर
जी
सर वो दूसरे लेक्चर का टाइम हो गया और सर ने मीटिंग स्टार्ट की
sorry let me quit. So next time inshallah I will start from the same. So I have taken your attendance and let me stop the recording.
सर वो कुछ स्टूडेंट्स कह रहे थे कि आप स्लाइड्स अगर शेयर कर दें
जी मैं
शायद
इसको
लास्ट लेक्चर की भी नहीं शेयर हुई
जी मैंने अभी एंटर किया, ये भी मैं कर देता हूँ। राइट,
ओके सर
अल्लाह हाफिज़।